Hello there, and welcome to Midnight Science. I'm so glad you found your way here tonight. Maybe the day has been long, or maybe you simply need a moment to let everything slow down. Either way, you're exactly where you need to be. Tonight, we're going to drift through the cosmos together, but we're not rushing anywhere. We'll move gently from star to star, learning about their births, their lives, their quiet deaths, and the beautiful mysteries they hold. Some facts might surprise you. Others might simply wash over you like waves on a shore, soft and rhythmic. And that's perfectly fine. If this kind of peaceful exploration helps you rest, consider liking and subscribing. It helps others find this quiet corner of the universe too. But for now, let your shoulders drop. Let your breathing deepen. Let the world outside fade just a little, because tonight we're going to look up at the stars and let them carry us gently towards sleep. Stars are born in clouds of dust and gas, in the cold, dark regions of space, far from any light. There are clouds, vast clouds of hydrogen and helium stretched across light years, drifting silently through the galaxy. These are stellar nurseries, places where stars begin. When a cloud becomes dense enough, gravity starts to pull it inward, slowly at first, then faster. The gas heats up as it compresses, atoms colliding more and more frequently. Eventually, the core becomes so hot, so dense, that hydrogen atoms fuse into helium. And in that moment, a star is born. Not with a bang, but with a gentle ignition. A glow that will last for millions, even billions of years. Every star you see in the night sky began this way, pulled from darkness into light by the patient hand of gravity. The sun is just an ordinary star when we look up during the day. The sun dominates our sky. Bright, warm, essential. It's easy to think of it as special, unique, but in truth, the sun is remarkably average. It's a yellow dwarf, a medium-sized star in the grand scheme of the cosmos. There are stars far larger, far brighter, and far more massive. And there are stars much smaller and dimmer too. The sun sits comfortably in the middle. It's not the hottest or the coolest, not the oldest or the youngest, just a steady, reliable star doing what stars do, fusing hydrogen into helium, radiating light and warmth into the void. And perhaps that's what makes it so beautiful. Not its uniqueness, but its ordinariness. A reminder that even the most extraordinary things in our lives can be, in the universe's eyes, wonderfully, peacefully normal. Stars come in many colors. If you've ever looked closely at the night sky, you might have noticed that not all stars look the same. Some shine with a cool bluish tint. Others glow warm and orange or even red. These colors aren't random. They tell us about the star's temperature. The hottest stars burn blue or white, with surface temperatures over 30,000 degrees Celsius. Cooler stars, like our sun, appear yellow, and the coolest stars of all glow red, with temperatures around 3,000 degrees. It's counterintuitive, isn't it? We think of red as hot and blue as cool, but in the language of stars, blue means scorching, and red means merely warm. Each color is a clue, a piece of the star's story written in light. And when you look up at the sky, you're seeing a rainbow of temperatures, a spectrum of stellar life painted across the darkness. The nearest star is over 4 light years away. After the Sun, the closest star to Earth is Proxima Centauri. It's a small red dwarf, quietly glowing in the southern sky. But even though it's our nearest neighbor, it's unimaginably far away. about 4.24 light years. That means if you could travel at the speed of light, it would still take over 4 years to reach it. With our current spacecraft, the journey would take tens of thousands of years. Space is vast in ways our minds struggle to grasp. The distances between stars are so great that even light, the fastest thing we know, takes years to cross them. And yet, the light from Proxima Centauri reaches us. Every photon that touches your eye began its journey over 4 years ago, traveling silently through the void, just to arrive here, now, and be seen by you. Some stars pulse like cosmic heartbeats. Not all stars shine with steady light. Some brighten and dim in regular rhythms, pulsing like hearts beating in the dark. These are called variable stars, and they change brightness for different reasons. Some swell and shrink as their outer layers expand and contract. Others are part of binary systems, where one star passes in front of the other, causing periodic eclipses. One famous type is the Cepheid variable, a massive star that pulses with remarkable regularity. Astronomers use these stars as cosmic measuring sticks because their pulsation period is directly related to their true brightness. By watching how they pulse, we can calculate how far away they are. In this way, the heartbeat of a distant star helps us map the universe. Slow, steady, rhythmic, a pulse that echoes across the galaxy. Stars spend most of their lives in a stable phase. After a star is born, it settles into a long, quiet period of stability. For stars like the Sun, this phase lasts billions of years. During this time, the star fuses hydrogen into helium in its core, releasing energy that pushes outward, balancing the inward pull of gravity. This balance, this equilibrium, is what keeps a star shining steadily. No violent changes, no dramatic shifts, just a slow, patient burn. The Sun has been in this phase for about 4.6 billion years, and it will remain there for another 5 billion more. Most of a star's life is spent this way, in calm persistence. It's a reminder that even in the cosmos, stability is the norm. The explosions and transformations we find so dramatic are brief moments in a much longer, quieter story. Red dwarfs can live for trillions of years. The smallest stars, known as red dwarfs, burn so slowly that they can live for an extraordinarily long time. While massive stars might only shine for a few million years, red dwarfs can last for trillions. That's longer than the current age of the universe by many times over. They sip their fuel carefully, converting hydrogen into helium at such a slow rate that they'll still be glowing long after larger stars have died and faded. In fact, because the universe is only about 13.8 billion years old, not a single red dwarf has yet reached the end of its life. Every red dwarf ever born is still shining. They are the ultimate survivors, small, dim, but patient beyond measure. In the far future, when most stars have gone dark, red dwarfs will still be there, the last embers in a cooling cosmos. Massive stars burn fast and die young. At the other end of the spectrum are the giants, stars dozens of times more massive than the Sun. These stars burn with incredible intensity, fusing elements at a furious pace. But their brightness comes at a cost. They exhaust their fuel quickly, sometimes in just a few million years. Where the Sun will shine for 10 billion years, a massive star might live for only 10 million. And when they die, they don't fade quietly. They explode. These are the supernovae cataclysmic events that can briefly outshine entire galaxies. In their final moments, massive stars forge the heaviest elements, scattering them into space. It's a short life, but a spectacular one. A blaze of glory that leaves behind not silence, but seeds. The raw materials for planets, for life, for everything that comes after. Stars are made mostly of hydrogen and helium. Look at a star, and you're looking at simplicity. Despite their size and brilliance, stars are made almost entirely of just two elements, hydrogen and helium. About 75% hydrogen, 24% helium, and only 1% everything else. Those trace amounts include carbon, oxygen, iron, and all the other elements we see around us. But in the heart of a star, it's mostly just the two lightest elements, fusing, burning, and releasing energy. This simplicity is part of what makes stars so elegant. They don't need complexity to shine, just pressure, heat, and time. And from that simple recipe, they create light, warmth, and eventually, through their deaths, the heavier elements that make up planets and people. The core of a star is unimaginably hot. At the center of a star, conditions are extreme. Temperatures reach 15 million degrees Celsius in the sun's core, and even higher in more massive stars. At these temperatures, atoms move so fast that when they collide, they can overcome the electromagnetic force that usually pushes them apart. They fuse, merging into new elements and releasing energy in the process. This is nuclear fusion, the engine that powers every star. The core is a furnace, a place where matter is transformed, where light is born. But we can't see it. The core is hidden beneath layers of gas, buried deep within the star's body. All we see is the surface, the photosphere, which is much cooler. The true fire burns in secret, deep inside, quietly fueling the glow we see from millions of miles away. Starlight takes thousands of years to escape the sun. When a photon is created in the sun's core, it doesn't immediately shoot out into space. Instead, it begins a long, chaotic journey. The interior of the sun is incredibly dense, packed with particles that absorb and re-emit photons constantly. Each photon bounces around, taking a random walk through the layers of the star. This journey can take anywhere from 10,000 to 170,000 years, depending on the path it takes. Only after this long migration does the photon finally reach the surface and stream out into space. From there, it takes just 8 minutes to reach Earth. So the sunlight warming your face right now was created long, long ago, deep in the sun's core. It spent millennia trapped inside, bouncing from atom to atom, before finally escaping to travel across the solar system and touch your skin. Stars rotate. Some incredibly fast stars spin. Just like planets, they rotate on their axes, though at vastly different speeds. Our sun rotates once every 27 days or so, a leisurely pace. But some stars spin much, much faster. Neutron stars, the collapsed cores of dead massive stars, can rotate hundreds of times per second. These are called pulsars, and they emit beams of radiation that sweep across space like lighthouse beams. Each time the beam points toward Earth, we detect a pulse. Some pulsars are so regular, they rival atomic clocks in their precision. And then there are young, massive stars that rotate so fast, their equators bulge outward, flattened by centrifugal force, spinning, whirling, turning. Even in the stillness of space, stars are always in motion. Some stars are part of binary systems. Many stars don't live alone. In fact, most stars in our galaxy are part of binary or multiple star systems, orbiting a common center of mass. These stellar companions can be close, orbiting each other in days or hours, or they can be far apart, taking centuries to complete a single orbit. Some binary stars are so close that they touch, transferring mass from one to the other in a delicate gravitational dance. Others are so distant, you might not even realize they're connected. When you look up at a single point of light, you might actually be seeing two stars, their light blended together. The universe, it turns out, prefers company. Stars are social, bound by gravity, orbiting in pairs, trios, even larger groups, moving through space together. Stars create elements through fusion. Inside a star, something miraculous happens. Hydrogen atoms, the simplest element, are fused together to form helium. As the star ages and its core grows hotter, it begins fusing helium into carbon and oxygen. In more massive stars, this process continues. Carbon fuses into neon, neon into magnesium, and so on, building heavier and heavier elements. Each fusion reaction releases energy, keeping the star shining. But it also builds the periodic table, atom by atom. Everything heavier than helium was made inside stars. The oxygen you breathe, the carbon in your body, the iron in your blood. All of it was forged in stellar furnaces, then scattered into space when those stars died. You are made of stardust, not poetically, but literally. The elements in your body were born in the hearts of ancient stars. A star's color tells us its age, young. Massive stars tend to burn blue and hot. As they age and exhaust their hydrogen, they can swell into red giants or supergiants, cooling and expanding. Smaller stars, like our Sun, will eventually become red giants too, before shedding their outer layers and leaving behind a white dwarf. The color of a star is a window into its life stage. Blue means youth and intensity. Yellow means middle age and stability. Red can mean either a cool, small star or an aging giant in his final years. And white dwarfs glow white hot, even as they slowly fade. Each hue is a chapter in the story of a star's life, written in the spectrum of light it emits. The sun will become a red giant one day. Our sun won't shine forever. In about 5 billion years, it will begin to run out of hydrogen in its core. When that happens, the core will contract and heat up, while the outer layers will expand dramatically. The sun will swell into a red giant, growing so large it may engulf Mercury, Venus, and possibly even Earth. Its surface will cool, glowing red instead of yellow. For a time, it will be hundreds of times larger than it is now, a vast glowing sphere dominating the sky. But this phase won't last long, cosmically speaking. Eventually, the sun will shed its outer layers, creating a beautiful planetary nebula. And at the center, a small dense core will remain, a white dwarf, slowly cooling over billions of years. The sun's death will be slow, quiet, and strangely beautiful. Neutron stars are incredibly dense. When a massive star explodes in a supernova, its core can collapse into a neutron star, an object so dense that a teaspoon of its material would weigh about 1 billion tons. Neutron stars are only about 20 kilometers across, roughly the size of a city, but they contain more mass than the sun. Their gravity is immense, their magnetic fields unimaginably strong. On their surface, the pull of gravity is so intense that if you dropped an object from just 1 meter above, it would hit the ground at millions of kilometers per hour. Time itself moves differently near a neutron star, slowed by the warping of space-time. These are among the most extreme objects in the universe, remnants of stellar death, packed with matter in a state we can barely comprehend. Stars can explode in brilliant supernovae. when a massive star reaches the end of its life. It goes out in one of the most energetic events in the universe. The core collapses in a fraction of a second, and the outer layers are blasted into space in a supernova explosion. For a few weeks, the dying star can shine as brightly as an entire galaxy, outshining billions of other stars combined. The explosion sends shockwaves rippling through space, triggering the formation of new stars in nearby gas clouds. It also scatters heavy elements into the cosmos, enriching the interstellar medium. These elements will one day become part of new stars, new planets, and perhaps new life. Supernovae are violent, yes, but they're also creative. They're the universe's way of recycling, transforming old stars into the building blocks of the future. White dwarfs are the remains of sun-like stars. After a star like our sun exhausts its fuel and sheds its outer layers, what remains is a white dwarf. This is the core of the star, no longer generating energy through fusion, just radiating away its leftover heat. White dwarfs are incredibly dense, about the size of Earth, but with the mass of the sun. They glow white-hot at first, but over billions of years they cool and dim, eventually becoming black dwarfs, cold, dark, and invisible. The universe isn't old enough yet for any black dwarfs to exist. Every white dwarf ever formed is still glowing somewhere, slowly fading. They're the final state of most stars, the quiet end of a long, bright life. Not an explosion, but a gentle fade into darkness. Stars twinkle because of Earth's atmosphere. On a clear night, stars seem to twinkle, sparkling and shimmering in the sky. But this isn't because the stars themselves are changing. It's because of our atmosphere. As starlight passes through layers of air with different temperatures and densities, it bends and refracts, causing the star's position to shift slightly. This creates the twinkling effect we see. Planets, on the other hand, don't twinkle as much. That's because they're close enough to appear as tiny disks rather than points of light, and the averaging effect smooths out the atmospheric distortion. If you were standing on the moon, where there's no atmosphere, stars would shine with steady, unblinking light. The twinkle is a gift from our planet, a reminder that even the light of distant suns must pass through our world to reach our eyes. Some stars are invisible to the naked eye. Of the billions of stars in our galaxy, only a few thousand are visible to the naked eye on a clear, dark night. The rest are too dim, too distant, or obscured by dust and gas. Even the brightest stars in our sky are just a tiny fraction of what's out there. Most stars are red dwarfs, small and faint, shining so dimly that they can only be seen with telescopes. There are also stars hidden behind clouds of interstellar dust, their light absorbed and scattered before it reaches us. And then there are stars so far away, their light hasn't had time to reach Earth yet. The night sky, for all its beauty, is just a glimpse. Beneath that tapestry of visible stars lies an even greater ocean of light, waiting to be discovered. Stars form in clusters. When a giant cloud of gas collapses, it doesn't usually form just one star, it forms many. Stars are born in clusters, sometimes dozens, sometimes thousands at a time. These stellar nurseries, like the Pleiades or the Orion Nebula, are among the most beautiful sights in the sky. Young stars still surrounded by glowing gas and dust shine together in tight groups. Over time, these clusters can drift apart as the stars go their separate ways, pulled by the galaxy's gravity. But for a while, They stay together, siblings in the cosmic sense, born from the same cloud, shining side by side. Some clusters are old, their stars ancient and red. Others are young, hot and blue. Each one is a snapshot of stellar birth, frozen in time. Supergiants are among the largest stars. Some stars are so large, they defy comprehension. Supergiants like Betelgeuse or VY Canis Majoris are hundreds or even thousands of times wider than the Sun. If you place Betelgeuse at the center of our solar system, it would extend past the orbit of Mars. These stars are rare, massive, and short-lived. They burn through their fuel quickly, and when they die, they explode in supernovae, leaving behind neutron stars or black holes. Supergiants are so bright that they can be seen from across the galaxy. But they're also unstable, pulsating and shedding mass into space. They're giants in every sense, towering over their smaller cousins, glowing fiercely and racing toward their inevitable end. The Sun produces energy through nuclear fusion. Deep in the Sun's core, 4 hydrogen nuclei are fused together to form one helium nucleus. This process releases a tiny amount of energy, but it happens trillions upon trillions of times every second. The cumulative effect is staggering. The Sun converts about 4 million tons of matter into energy every second. Following Einstein's equation, E equals mc squared. That energy radiates outward, eventually reaching the surface and streaming into space as light and heat. It's this fusion process that powers the Sun, and by extension powers life on Earth. Every ray of sunlight, every photon, is a product of nuclear reactions deep inside the star. The Sun is a nuclear reactor, but one perfectly balanced, stable, and life-giving. Stars have life cycles like living things. Stars are born, live, and die. They begin in clouds of gas and dust, ignite through nuclear fusion, spend most of their lives in a stable phase, and eventually exhaust their fuel. What happens next depends on their mass. Small stars become white dwarfs. Massive stars explode and leave behind neutron stars or black holes. The heaviest stars collapse into black holes, regions of space-time where gravity is so strong, not even light can escape. Each stage is a chapter in the star's story, a journey from darkness through light and back to darkness again. But even in death, stars are generous. They return their material to the cosmos, seeding space with the elements needed for new stars, new planets, new life. The cycle continues, endlessly, beautifully. Stars influence the formation of planets. Stars don't exist in isolation. Around many of them, planets form from the leftover material in the protoplanetary disk, a swirling cloud of gas and dust that remains after the star's birth. Particles collide and stick together, gradually building up into larger and larger objects, first pebbles, then boulders, then planetesimals, and finally planets. The star's gravity shapes the disk, its radiation clears away gas, and its light warms the surfaces of the newborn worlds. In this way, stars are architects, not just of light, but of worlds. Our own Sun played this role 4.6 billion years ago, when Earth and the other planets coalesced from the debris of the solar nebula. Every planet is a child of its star, shaped by its warmth and gravity. The brightest star in the sky is Sirius. If you look up on a clear winter night, you might see a brilliant point of light low on the horizon. That's Sirius, the dog star, the brightest star in Earth's night sky. Sirius is actually a binary system, consistent of a bright main sequence star and a faint white dwarf companion. It's only about 8.6 light-years away, relatively close in cosmic terms, which is part of why it appears so bright. Sirius has been important to many cultures throughout history, used as a seasonal marker and a navigational guide. Its name comes from the Greek word for glowing or scorching, and is easy to see why. Sirius shines with a steady, pure light, a beacon in the darkness, reminding us that even among billions of stars, some stand out. Stars can merge together. In close binary systems, where two stars orbit each other tightly, something dramatic can happen. If they're close enough, they can transfer mass back and forth, or even collide and merge. When two stars merge, the result is usually a hotter, more massive star, sometimes with unusual properties. These merger events can trigger bursts of activity, create exotic stellar objects, or even lead to supernova explosions. The universe is not a static place. Stars don't just sit in the sky. They interact, dance, and sometimes embrace, becoming one. It's a process that takes thousands or millions of years, but when it happens, it can reshape the night sky. Stars are born from the remnants of older stars. The universe recycles everything. When a star dies, it doesn't vanish. Its material is returned to space, mixing with clouds of gas and dust. Those clouds can then collapse again, forming new stars. In this way, each generation of stars is built from the ashes of the last. The atoms in a young star today might once have been part of an ancient giant that exploded billions of years ago. This cycle has been repeating since the first stars formed, enriching the galaxy with heavier elements over time. The Sun, and by extension Earth, are part of this great cosmic cycle. We're all made of recycled star stuff, pieces of the past woven into the present. Some stars emit jets of material. Certain stars, especially young ones and those in binary systems, can launch powerful jets of material into space. These jets are streams of gas and plasma, accelerated to incredible speeds by magnetic fields and radiation pressure. They can stretch for light years, carving tunnels through the surrounding gas and dust. In young stellar objects, these jets help shed excess angular momentum, allowing the star to continue forming. In binary systems, matter falling onto a compact object like a neutron star or black hole can create jets as well. These jets are visible in many wavelengths, glowing brightly in radio and X-ray light. They're reminders that stars aren't passive. They're active, dynamic, constantly shaping their environment. Red giants are stars in their final stages. When a star like the Sun exhausts the hydrogen in its core, it begins to change. The core contracts and heats up, while the outer layers expand and cool. The star becomes a red giant, vastly larger than it was before. During this phase, the star fuses helium into carbon and oxygen, prolonging its life for a time. But this is a temporary reprieve. Red giants are unstable, pulsating and shedding mass into space. Eventually, they'll eject their outer layers entirely, creating a planetary nebula, and leave behind a white dwarf. Red giants are beautiful in their way, glowing softly with a deep, ruddy light. They're stars saying goodbye, swelling up one last time before fading away. Stars are powered by gravity at its most fundamental level. A star is a battle between two forces. Gravity pulls inward, trying to compress the star into the smallest possible space. But nuclear fusion in the core creates outward pressure, pushing back against gravity's pull. As long as these forces are balanced, the star remains stable. But when the fuel runs out, gravity wins. The core collapses, and the star enters its final phase, whether that's becoming a white dwarf, a neutron star, or a black hole. Gravity is the architect of stars, the force that brings them into being and ultimately dictates their fate. Without it, there would be no stars, no light, no life, just cold, empty space. Stars shine for billions of years. It's hard to grasp just how long a star can shine. Our sun has been burning for 4.6 billion years, and it's only about halfway through its life. Smaller stars can last even longer, glowing faintly for trillions of years. Even massive stars, which live fast and die young, still shine for millions of years. That's longer than human civilization has existed, longer than most species last. Stars are patient. They don't rush. They simply burn steadily and continuously for timescales that dwarf our own. And yet, to the universe, even a star's lifetime is fleeting. Everything has a beginning and an end, even light itself. Stars can have magnetic fields, just like Earth. Many stars have magnetic fields created by the movement of charged particles in their interiors. These fields can be weak, like the sun's, or incredibly strong, like those found in neutron stars. Magnetic fields can create sunspots, dark patches on a star's surface where the field inhibits convection. They can also launch flares and coronal mass ejections, bursts of energy and particles that stream into space. In neutron stars, the magnetic field is so intense it can tear apart atoms and bend light. These fields are invisible, but their effects are profound, shaping the star's behavior and influencing everything around it. Constellations are patterns, not groups. When we look up and see constellations, it's easy to imagine that the stars are grouped together in space. But they're not. The stars in a constellation can be vastly different distances from Earth, scattered across hundreds or thousands of light years. They only appear close together because of our perspective. If you travel to another star, the constellations would look completely different. They're patterns imposed by human imagination, stories written in the sky, and yet they're meaningful. For thousands of years, people have looked up, connected the dots, and told stories about the stars. The constellations aren't real in a physical sense, but they're real in the way they've shaped our culture, our navigation, and our sense of wonder. Stars can be eclipsed by planets. Sometimes, when a planet passes directly between us and its star, we see the star's light dim slightly. This is called a transit, and it's one of the primary ways astronomers discover exoplanets. By carefully measuring the star's brightness, they can detect the tiny shadow cast by the planet. From that shadow, they can calculate the planet's size, orbit, and sometimes even its atmosphere. It's a delicate dance, one that requires precise measurements and patient observation. But it works. We've discovered thousands of planets this way, orbiting distant stars, revealing just how common planetary systems are. Each dimming of a star is a clue, a whisper across the void saying, there are worlds here. Stars form patterns in galaxies. Galaxies aren't just random collections of stars. They have structure. Spiral galaxies, like the Milky Way, have arms made of young, hot blue stars and glowing gas. Elliptical galaxies are filled with older, redder stars, with little active star formation. Irregular galaxies are chaotic, often shaped by collisions or gravitational interactions. The distribution of stars tells a story about the galaxy's history, how it formed, how it evolved, and what it's become. Stars trace out the shape of the cosmos, lighting up the dark matter scaffolding that holds everything together. In their patterns, we see the grand design of the universe woven in light. Stars die in different ways. Not all stars die the same way. Small stars, like red dwarfs, will eventually cool and fade, becoming black dwarfs after trillions of years. Medium stars, like the Sun, will swell into red giants, shed their outer layers, and leave behind white dwarfs. Massive stars will explode in supernovae, scattering their material across space and leaving behind neutron stars. The most massive stars of all will collapse directly into black holes, vanishing from view. Each death is shaped by the star's mass, its composition, and its history. And each leaves behind something different, a remnant, a nebula, or just the echo of light fading into the dark. The first stars had no heavy elements. The very first stars, born just a few 100 million years after the Big Bang, were different from the stars we see today. They formed from pure hydrogen and helium with no heavy elements at all. No carbon, no oxygen, no iron. These stars, called population 3 stars, would have been massive, hot and short-lived. They burned brightly for just a few million years, then exploded, seeding the early universe with the first heavy elements. Those elements became part of the next generation of stars, which in turn created even more. Over billions of years, the universe has been enriched, generation by generation. The stars we see today, including the Sun, are made from the ashes of those first stars. Their descendants, carrying the legacy of light from the dawn of time. Stars help us measure cosmic distances. Without stars, we wouldn't be able to map the universe. Certain types of stars, like Cepheid variables, have a predictable relationship between their brightness and their pulsation period. By observing how they pulse, astronomers can calculate their true luminosity. Then, by comparing that to how bright they appear from Earth, they can determine how far away they are. It's like using a cosmic ruler, one that stretches across millions of light years. Other stars, like supernovae, serve a similar purpose, acting as standard candles that help us measure even greater distances. In this way, stars are not just sources of light, they're guideposts, markers in the vast expanse of space, helping us find our way. Stars produce sound waves we can't hear inside a star. Sound waves ripple through the layers of gas, driven by convection and pressure changes. These waves are too low in frequency for human ears to detect, but they're there, pulsing through the star's interior. Astronomers study these oscillations using a technique called asteroseismology, essentially listening to the star's vibrations by watching how its surface moves. From these subtle motions, they can learn about the star's internal structure, its age, and its composition. In a way, stars are singing, each with its own unique frequency. And by listening carefully, we can hear the music of the cosmos, a symphony played in the deep bass notes of distant suns. Stars create their own weather. Just like Earth has weather, so do stars. The sun's surface is constantly in motion, with hot gas rising, cooling, and sinking in a process called convection. This creates patterns on the surface, like granules, each about the size of a small country, bubbling up and disappearing within minutes. The sun also has storms, solar flares, massive eruptions of energy that blast radiation into space. There are coronal mass ejections, where huge chunks of the sun's outer atmosphere are flung into the solar system. These events can affect Earth, causing auroras, disrupting satellites, and even knocking out power grids. Stars aren't calm. They're turbulent, dynamic, filled with movement and change. They have seasons, cycles, and storms, all driven by the endless churn of nuclear energy. Ancient starlight carries messages from the past. When you look at a star, you're not seeing it as it is now. You're seeing it as it was when the light left its surface. For nearby stars, that might be just a few years ago. But for distant stars, it could be hundreds, thousands, or even millions of years. The light has been traveling all that time, crossing the emptiness of space, just to reach your eyes tonight. In a very real sense, looking at the stars is looking into the past. Some of the stars you see may no longer exist, having already died and faded, but their light continues on, a messenger carrying news from long ago. The night sky is not a snapshot of now, but a gallery of history, each star a window into a different moment in time. Stars can wobble because of planets. When a planet orbits a star, it doesn't just move in a circle while the star stays still. Both the planet and the star orbit their common center of mass, like two dancers spinning around each other. For massive planets orbiting close to their stars, this wobble can be detected from Earth. Astronomers measure the star's motion by watching for tiny shifts in its light, caused by the Doppler effect. As the star moves toward us, its light shifts slightly bluer. As it moves away, it shifts redder. By measuring these shifts, scientists can infer the presence of planets, even if they can't see them directly. It's a delicate technique, requiring precision and patience. But it works. Through these wobbles, we've discovered countless worlds, hidden in the dance of distant stars. Stars can steal material from each other. In close binary systems, where two stars orbit tightly, one star can pull material from its companion. This happens when one star swells into a giant, and its outer layers drift close enough for the other star's gravity to capture them. The material streams from one star to the other, forming a glowing accretion disk. Sometimes this transfer is steady. Other times, it triggers violent outbursts, sudden flashes of light as the stolen gas heats up and ignites. These interactions can dramatically alter both stars, changing their masses, compositions, and futures. In the cosmos, even stars can be thieves, quietly siphoning away their neighbor's substance, bound together by gravity and fate. The sun has an 11-year cycle. The sun isn't constant. It goes through an 11-year cycle of activity, driven by its magnetic field. During solar maximum, the sun is covered in sunspots, and solar flares and coronal mass ejections are common. During solar minimum, the surface is quieter, with fewer spots and less activity. This cycle affects space weather, which in turn can affect satellites, power grids, and even communication systems on Earth. Auroras are more common during solar maximum, painting the skies with green and pink light. The cycle is driven by the sun's internal dynamo, the movement of charged particles creating and destroying magnetic fields. It's a rhythm, a pulse, a heartbeat that the sun follows over and over, year after year. Stars are classified by their spectra. Astronomers classify stars using a system based on their spectra, the rainbow of light they emit. This system, called spectral classification, sorts stars into categories labeled O, B, A, F, G, K, and M. O stars are the hottest and bluest. M stars are the coolest and reddest. Our Sun is a G-type star, right in the middle. Each spectral type reveals information about the star's temperature, composition, and stage of life. By studying a star's spectrum, astronomers can tell what elements it contains, how fast it's spinning, and whether it has a magnetic field. The spectrum is like a fingerprint, unique and revealing. In the light of a star, its entire story is written, waiting to be read. Stars can be magnified by gravity. Sometimes, a massive object like a galaxy or galaxy cluster sits between us and a distant star. The object's gravity bends the light from the star, acting like a lens. This phenomenon, called gravitational lensing, can magnify the distant star, making it appear brighter or even creating multiple images. In rare cases, a single star can be magnified enough to be seen across billions of light years, something that would normally be impossible. Gravitational lensing is a powerful tool, allowing astronomers to study distant objects and measure the distribution of dark matter. It's a reminder that in the universe, even light can be bent, shaped, and focused by the invisible hand of gravity. Some stars explode more than once. Certain stars can explode repeatedly. These are called novae, and they occur in binary systems where a white dwarf pulls material from a companion star. As gas accumulates on the white dwarf's surface, it compresses and heats up. Eventually, it ignites in a runaway fusion reaction, causing the star to brighten suddenly, a nova. But unlike a supernova, the white dwarf survives. The explosion blows off the accumulated material, and the process can start again. Some novae recur every few years or decades. Others take centuries. Each explosion is a brief, brilliant flash, a star flaring to life, then settling down, only to flare again. It's a cycle of violence and calm, repeated across the ages. Stars influence each other across vast distances. Even stars that are far apart can influence one another. A massive star's gravity can trigger star formation in a nearby cloud, compressing it enough to start the collapse. A supernova's shockwave can sweep through a region, compressing gas and sparking new generations of stars. Stars in clusters can interact gravitationally, flinging each other into different orbits, or even ejecting some into interstellar space. The universe is not a collection of isolated objects. It's a web of interactions, where every star affects and is affected by its neighbors. Even across light years, the connection remains, subtle but real. Stars can have rings of dust. Just as planets can have rings, so can stars. Young stars, in particular, are often surrounded by disks of dust and gas, the remnants of their formation. These disks are where planets form, particles sticking together to build worlds. But even older stars can have rings, created by collisions between asteroids or comets, or by material ejected from the star itself. These rings glow faintly in infrared light, heated by the star's radiation. They're beautiful, delicate structures, reminders that stars don't exist in a vacuum. They're surrounded by debris, the raw materials of planetary systems, waiting to be shaped into something new. The sun loses mass every second. Even as it shines, the sun is slowly losing mass. Every second, about 4 million tons of matter are converted into energy through nuclear fusion. That energy radiates away into space as light. Additionally, the sun constantly blows off material in the solar wind, a stream of charged particles flowing outward from its surface. Over billions of years, the sun has lost a tiny fraction of its original mass. But don't worry, it has plenty left. The loss is gradual, barely noticeable on human timescales. Still, it's a reminder that nothing is permanent. Even the sun, stable and enduring, is slowly giving itself away, one photon, one particle at a time. Stars can have planets in their habitable zones. Around many stars, there's a region called the habitable zone, where conditions might be just right for liquid water to exist on a planet's surface. Not too hot, not too cold. This zone depends on the star's temperature and brightness. For a hot, bright star, the habitable zone is far out. For a cool, dim star, it's much closer. Finding planets in this zone is one of the primary goals of exoplanet research, because where there's liquid water, there might be life. Not every planet in the habitable zone is habitable, but it's a good place to start looking. And with each discovery, we learn more about the diversity of worlds and the potential for life beyond Earth. Stars can have spots like the sun, just as the sun has sunspots. Other stars have star spots, dark patches caused by magnetic fields inhibiting the flow of hot gas to the surface. These spots are cooler than the surrounding area, so they appear darker. By observing how a star's brightness changes as it rotates, astronomers can map the locations and sizes of these spots. Some stars have enormous spots, covering a significant fraction of their surface. Others have small, fleeting ones. Star spots tell us about a star's magnetic activity, rotation rate, and internal dynamics. They're scars of magnetic turbulence, visible marks of the forces churning deep inside the star. Binary stars can eclipse each other. In some binary star systems, the two stars orbit in such a way that, from our perspective, they pass in front of each other. When this happens, we see an eclipse. The combined light of the system dims as one star blocks the other. By carefully timing these eclipses and measuring how much light is blocked, astronomers can determine the star's sizes, masses, and orbits with incredible precision. These eclipsing binaries are natural laboratories, allowing us to study stars in ways that wouldn't be possible otherwise. Each eclipse is a brief alignment, a moment when two stars, locked in their eternal dance, line up perfectly with Earth, revealing their secrets. Stars lose their outer layers as they age. As stars grow old, they become less stable. Their outer layers can puff up and drift away, carried off by stellar winds or pulsations. This process creates beautiful structures called planetary nebulae, glowing shells of gas surrounding the dying star. The name is misleading. They have nothing to do with planets. Early astronomers thought they looked like planets through their telescopes. In reality, they're the final exhalations of stars like the sun, shedding their outer envelopes before settling down as white dwarfs. Each nebula is unique, shaped by the star's rotation, magnetic field, and binary companions. They glow in vibrant colors, lit from within by the ultraviolet light of the dying star. Beautiful, fleeting, and quietly tragic. Stars generate energy for billions of years without refueling. A star is the ultimate engine. Once it ignites, it can run for billions of years without any external fuel source. Everything it needs is already inside, locked within its own mass. The sun, for example, has enough hydrogen to keep fusing for another 5 billion years. It doesn't need to consume anything from outside. It simply converts its own matter into energy, slowly, steadily, patiently. This self-sufficiency is remarkable. A star is a closed system, powered entirely by the transformation of its own substance. And when the fuel finally runs out, the star doesn't stop abruptly. It changes, evolves, and eventually fades, having given everything it had to give. Stars help us understand the age of the universe. By studying the oldest stars, astronomers can estimate the age of the universe. Globular clusters, ancient groups of stars that orbit the outskirts of galaxies, contain some of the oldest known stars. By analyzing their light, measuring their composition, and modeling their evolution, scientists can calculate how long they've been shining. These stars are typically around 12 to 13 billion years old, which aligns with the age of the universe itself, about 13.8 billion years. These ancient stars are fossils, relics from the early days of the cosmos. They've been shining since before most galaxies fully formed, quiet witnesses to nearly the entire history of the universe. Stars create shock waves when they explode. When a massive star goes supernova, the explosion sends a shock wave rippling outward at thousands of kilometers per second. This shock wave compresses and heats the surrounding gas, creating a glowing shell that expands for thousands of years. Over time, the shock slows and the remnant cools, but it remains visible for millennia. These supernova remnants are some of the most spectacular structures in the galaxy. They're also important. The shock wave can trigger new star formation, compress nearby gas clouds, and enrich the interstellar medium with heavy elements. In this way, the death of one star becomes the birth of many others. The shock doesn't just destroy, it creates. Stars can orbit supermassive black holes. At the center of most galaxies, including our own Milky Way, lies a supermassive black hole. Stars near the galactic center orbit this black hole, some at incredible speeds. Astronomers have tracked these stars for decades, watching them complete their orbits. One star, called S2, whips around the Milky Way's central black hole in just 16 years, reaching speeds of over 7,000 kilometers per second. By studying these orbits, scientists can measure the black hole's mass and test the laws of physics in extreme gravitational fields. These stars are like cosmic test particles, tracing the shape of space-time around one of the universe's most mysterious objects. Some stars are born alone. Not all stars are born in clusters. Some form in isolation, in small, quiet clouds of gas. These solitary stars drift through the galaxy without siblings, never part of a crowded nursery. They grow up alone, shining in the dark, surrounded only by the cold, empty space between stars. Our sun may have been born in a cluster, but it's now alone, its siblings scattered long ago. In the vastness of the galaxy, many stars wander solo, unaccompanied by companions, moving through the night in quiet solitude. There's a certain poetry to that. A lone star burning steadily, lighting a small patch of the cosmos, asking nothing in return. Stars can be used to navigate. For thousands of years, humans have used stars to find their way. Sailors navigated by the stars, using constellations and the North Star to guide their ships across featureless oceans. The stars don't move relative to each other on human timescales, so they're reliable markers. Even today, with GPS and modern technology, celestial navigation is still taught and used. The stars are constant, predictable, and always there, shining down from the same positions night after night. In a changing world, they offer stability, a reminder that some things endure. When everything else is uncertain, you can still look up and find your way home. Stars produce neutrinos deep in a star's core. Nuclear fusion produces not just energy and light, but also neutrinos, tiny, nearly massless particles that barely interact with matter. Trillions of neutrinos pass through your body every second, most of them coming from the sun. They zip through the earth, through walls, through everything, almost never stopping. Detecting neutrinos is incredibly difficult, but scientists have built massive detectors deep underground to catch a few. By studying solar neutrinos, we've learned about the fusion processes happening inside the sun, confirming our models of stellar physics. Neutrinos are ghostly messengers, carrying information from the heart of the star directly to us, unimpeded by the layers of gas above. Stars can flare unexpectedly. Some stars, especially young ones and red dwarfs, can produce sudden, intense flares, bursts of energy far more powerful than anything the sun produces. These flares release enormous amounts of radiation, sometimes brightening the star by several magnitudes in just minutes. The flares are driven by magnetic reconnection, where twisted magnetic field lines suddenly snap and release their stored energy. For planets orbiting flare stars, these events can be dangerous, stripping away atmospheres or sterilizing surfaces with radiation. But they're also fascinating, windows into the extreme magnetic activity that some stars experience. Each flare is a reminder that stars, for all their steadiness, can be unpredictable. Stars have convection zones inside many stars, including the sun. There's a region where energy is transported by convection, hot gas rising and cool gas sinking, like water boiling in a pot. This convection zone lies beneath the star's surface, churning and mixing the layers above the core. The motion of charged particles in this zone generates magnetic fields, which in turn drive much of the star's surface activity, sunspots, flares, and prominences. Without convection, stars would be much calmer, more static, but convection makes them dynamic, constantly moving, always changing. It's a hidden engine, invisible from the outside, but driving much of what we see. Stars can change brightness over time. Not all stars shine with constant light. Many are variable, changing brightness over days, weeks, or years. Some pulsate, swelling and shrinking rhythmically. Others are eclipsed by companions. Some vary because of star spots rotating in and out of view, and a few change for reasons we don't fully understand. By studying these variations, astronomers learn about the star's structure, composition, and evolution. Each fluctuation tells a story. Variability isn't a flaw, it's a feature, a sign that the star is alive, active, responding to the forces within and around it. The night sky isn't static, it's breathing, pulsing, changing, if you watch closely enough. Stars have coronas. Above a star's surface lies a thin, incredibly hot layer called the corona. For the sun, the surface temperature is about 5,500 degrees Celsius, but the corona reaches over 1,000,000 degrees. Why the corona is so much hotter than the surface is still one of astronomy's enduring mysteries. It may be heated by magnetic fields, by waves propagating through the atmosphere, or by a combination of factors. The corona is visible during a total solar eclipse as a glowing halo around the darkened sun. It's also the source of the solar wind, the stream of charged particles that flows outward through the solar system. This ghostly crown is part of every star, a shimmering, superheated atmosphere extending far beyond the visible surface. Some stars orbit in triple systems. Binary stars are common, but some stars go one step further, forming triple systems. In these arrangements, one star might orbit a close binary pair, or all three might orbit a common center in complex interlocking paths. These systems are gravitationally stable, sometimes for billions of years, though they can be chaotic, with orbits slowly shifting over time. For planets in triple star systems, the sky would be extraordinary. Instead of one sun, there might be two or three, rising and setting at different times, casting multiple shadows. Triple systems are rarer than binaries, but they're out there. Complex dances of light and gravity playing out across the galaxy. Stars are separated by immense distances. Even in our cosmic neighborhood, stars are incredibly far apart. The nearest star to the Sun, Proxima Centauri, is about 4.24 light-years away. That's roughly 40 trillion kilometers. If the Sun were the size of a grapefruit, Proxima Centauri would be another grapefruit over 2,500 kilometers away. Space is vast, and stars are tiny islands of light scattered across an ocean of darkness. Most of the universe is empty. The distances are so great that even light traveling at 300,000 kilometers per second takes years to cross the gaps. In this emptiness, stars are rare and precious, beacons in the void, shining alone. Stars produce cosmic rays. When massive stars explode in supernovae, they accelerate particles to nearly the speed of light. These particles, mostly protons, are called cosmic rays. They stream through the galaxy, bombarding everything in their path, including Earth. Our atmosphere shields us from most of them, but a few make it to the surface. Cosmic rays can affect electronics, contribute to cloud formation, and even pose a hazard to astronauts in space. They're also valuable scientific tools, carrying information about the supernova that created them and the magnetic fields they pass through. These invisible particles are constant travelers, racing through space at unimaginable speeds, remnants of stars long dead. Stars anchor planetary systems. A star is the gravitational center of its planetary system. Planets, asteroids, comets, all orbit the star, held in place by its gravity. The star's mass determines the shape and size of the orbits, and its light warms the surfaces of its worlds. Without the star, the planets would drift off into space, untethered and cold. In this way, stars are anchors, points of stability in the chaos of space. They hold their families together, providing light, warmth, and structure. Every planetary system is built around a star, and every world story begins with the light of its sun. Stars can steal planets from other stars. In dense star clusters, where stars pass close to one another, gravitational interactions can shuffle planets around. A planet orbiting one star might be pulled away by a passing neighbor, captured into a new orbit, or a close encounter might eject a planet entirely, sending it drifting through interstellar space as a rogue world. These events are rare, but they happen. In the crowded nurseries where stars are born, planets can change hands, orphaned and adopted in the slow dance of gravity. It's a reminder that planetary systems aren't always permanent. They can be disrupted, reshaped, or torn apart by the stars around them. Stars contribute to the cosmic background. The universe is not completely dark. Even in the emptiest regions of space, there's a faint glow, the extragalactic background light, created by all the stars that have ever shone. This light has been traveling for billions of years, blending together into a diffuse haze. It's incredibly faint, far below what the human eye can see, but is there, a collective glow from trillions of stars across cosmic history. Every star adds to this background a tiny contribution to the universe's luminosity. When a star dies, its light doesn't vanish instantly. It continues outward, joining the sea of ancient photons that fills the cosmos. Stars are fossils of the early universe. Old stars, particularly those in globular clusters, are like time capsules. They formed billions of years ago, when the universe was young, and their composition reflects the chemistry of that early era. By studying these ancient stars, astronomers can learn about the conditions in the early universe, how the first elements were distributed, and how galaxies evolved over time. These stars have witnessed nearly everything: the formation of galaxies, the birth and death of countless other stars, the slow march of cosmic time. They're survivors, carrying memories of a universe very different from the one we see today. Stars illuminate the universe. Without stars, the universe would be dark. No light, no warmth, no color. Stars are the primary source of illumination in the cosmos, transforming mass into energy and scattering light across billions of light years. They light up nebulae, illuminate planets, and guide our gaze through the night. Even the faintest star contributes to the glow, a tiny spark in the vast darkness. Together, stars turn the universe into something visible, something knowable. They don't just exist, they reveal. They make the invisible visible, the distant near, and the dark bright. Stars form heavier elements through neutron capture. In the final stages of a massive star's life, as it runs out of fuel, it can create elements heavier than iron through a process called neutron capture. Neutrons are added to atomic nuclei, building up heavier and heavier elements. There are two main types: slow neutron capture, which happens over long timescales, and rapid neutron capture, which occurs during supernova explosions. This rapid process, called the RNE process, is responsible for creating many of the heaviest elements in the universe, including gold, platinum, and uranium. Every atom of gold on Earth was likely forged in a supernova or neutron star merger, created in the final, violent moments of a dying star. Stars can live in the halo of a galaxy. Not all stars are part of a galaxy's disk or bulge. Some live in the halo, a vast, diffuse region surrounding the galaxy. These halo stars are often old, metal-poor, and move on highly elliptical orbits that take them far above and below the galactic plane. They may be remnants of smaller galaxies that were absorbed long ago, or they might have been ejected from the disk by gravitational interactions. Halo stars are wanderers, moving through empty space, far from the crowded regions where most stars reside. They're lonely, but they're free, tracing long, sweeping paths through the darkness. Stars are born at different rates in different galaxies. Not all galaxies make stars at the same pace. Some, like spiral galaxies, are actively forming new stars, with glowing regions of ionized gas marking stellar nurseries. Others, like elliptical galaxies, have little or no ongoing star formation, their gas supplies exhausted or stripped away. The rate of star formation depends on the availability of cold gas, the galaxy's history of mergers, and the influence of the central black hole. Some galaxies go through bursts of intense star formation, creating thousands of stars in a short period. Others are quiet, their star-making days long behind them. The universe is diverse, and so are the rhythms of stellar birth. Stars influence the chemistry of the universe. Every time a star dies, it releases its processed material back into space. This material, enriched with heavy elements, mixes with the interstellar medium and becomes part of the next generation of stars. Over billions of years, this process has gradually increased the metallicity of the universe, the abundance of elements heavier than hydrogen and helium. The first stars had almost no metals. The stars of today are rich with them. This chemical evolution is a slow, cumulative process, driven by countless stellar deaths. Each star's contribution is small, but together they've transformed the composition of the cosmos. Stars can be lensed into arcs and rings. When a massive object like a galaxy cluster lies between us and a distant star or galaxy, its gravity can bend the light into arcs, rings, or multiple images. This gravitational lensing creates beautiful, distorted shapes, like cosmic funhouse mirrors. These lensed images allow astronomers to study objects that would otherwise be too faint or distant to see. They also provide information about the mass distribution of the lensing object, including the presence of dark matter. Einstein's theory of general relativity predicted this effect, and today, it's a powerful tool for exploring the universe. Even light, the fastest traveler, can be bent and shaped by gravity's hand. Some stars have been ejected from their galaxies. Occasionally, a star can be flung out of its galaxy entirely, sent hurtling into intergalactic space at incredible speeds. This can happen during close encounters with other stars, or when a binary system near a supermassive black hole is disrupted, with one star captured and the other ejected. These hypervelocity stars travel at thousands of kilometers per second, fast enough to escape the galaxy's gravitational pull. They're outcasts, doomed to wander the void between galaxies, forever separated from their birthplace. But they're not alone in the darkness. They carry with them the light of their home, a lone spark drifting through the cosmic night. Stars help regulate galactic ecosystems. Stars don't just passively exist within galaxies. They actively shape their environment. Young, massive stars emit intense radiation that ionizes surrounding gas, creating glowing nebulae. Stellar winds and supernova explosions inject energy into the interstellar medium, heating it and creating bubbles and shells. This feedback can suppress or trigger star formation, regulate the growth of galaxies, and even drive gas out of galaxies entirely. Stars are not isolated. They're part of a complex, interconnected system where each star's life and death affects the whole. The galaxy is an ecosystem, and stars are its key inhabitants. Stars have been observed for thousands of years. Humans have watched the stars for as long as we've existed. Ancient civilizations tracked their movements, recorded eclipses, and used them to measure time and navigate. The stars were gods, heroes, and stories written across the night sky. Today, we understand them differently, not as divine beings, but as physical objects, governed by the laws of physics. And yet, the sense of wonder remains. We still look up, still feel small beneath their light, still find meaning in their patterns. The stars connect us to our ancestors, to everyone who has ever looked up and wondered what lies beyond. Stars will eventually fade away. One day, in the unimaginably distant future, the last star will die. Star formation will cease as galaxies run out of gas. Existing stars will burn out one by one. First the massive ones, then the medium ones, and finally, trillions of years from now, the last red dwarfs. The universe will grow dark, lit only by the faint glow of cooling white dwarfs and the occasional flash of black hole radiation. This is called the degenerate era, a time when stars are just memories. But that's so far in the future, it's almost meaningless. For now, stars fill the sky, and they will continue to do so for billions of years. There's still so much time left for light. Stars remind us of our place in the cosmos. When you look up at the stars, you're looking at something ancient, vast, and beautiful. You're seeing light that has traveled across space and time to reach you. You're witnessing the slow burn of nuclear fusion, the birth and death of worlds, the endless cycles of the universe. And in that moment, you're part of it all. You're made of the same atoms that stars create. You're warmed by the same fusion that powers the sun. You're connected through light and matter and time to everything out there. The stars aren't just distant objects. They're part of your story, and you're part of theirs. And now, as we near the end of our journey, let the stars fade gently from your mind. Let them become a soft glow at the edge of thought, a quiet presence rather than a sharp focus. We've drifted through stellar nurseries and supernova remnants, through pulsars and red giants, through the birth and death of light itself. We've learned that stars are more than distant suns. They're factories, timekeepers, storytellers, and ancestors. They're the reason we exist, and the reason the universe is filled with light. Somewhere tonight, a new star is being born. Somewhere, an old one is taking its final breath. And between those moments, billions of stars are simply shining, patiently, steadily, as they have for eons. They ask nothing of us. They simply are. So as you close your eyes, imagine yourself floating gently among them, not rushing, not seeking, just drifting. You're safe here, cradled by the light of ancient suns, surrounded by the quiet music of the cosmos. Let your breathing slow. Let your body sink deeper into rest. Let the stars watch over you as they've watched over everything, calm, eternal, and softly glowing. You don't need to remember every fact. You don't need to hold on to anything. Just let it all wash over you like starlight on water, gentle and warm. The universe is vast, but you are here, resting, breathing, part of the endless cycle of matter and energy. And in this moment, that's enough. Sleep well, traveler. The stars will still be there tomorrow, patiently shining, waiting for you to look up once more. Thank you for spending this time here, drifting through the cosmos with me. If this helped you rest or sparked a quiet wonder, consider liking and subscribing. There are always more journeys to take, more mysteries to explore, one sleepy soul at a time. Good night.